Hello and welcome. I'm Sankar Subramanian, and I'm glad we can come together online to explore today's topic. I have over 20 years of experience in control and automation systems, bringing together hardware and software expertise in areas such as semiconductor lasers, fiber optic transceivers, and electric vehicle R&D and manufacturing. My work has often been about integrating precise engineering with intelligent, reliable automation. Over the past few years, I've been deeply involved in exploring how modern AI can be combined with robust programming tools to solve real world industrial challenges. Rust, with its focus on safety, speed, and concurrency, has quickly become a powerful choice of building high performance and reliable systems. In the system, we will be look at how AI-powered machine vision in Rust can deliver not only accuracy and efficiency, but also the scalability and suitability, making it a strong option for next generation automation. Over the next few minutes, I will share key concepts, real-world examples, key takeaways you can apply to your own work. Let's get started. AI-powered mission in Rust, transforming EV manufacturing quality and automation. The imperative of advanced mission system in EV manufacturing. Electrical, electric vehicle represents a fundamental shift in automotive design and manufacturing complexity due to its higher component density, requiring multi-micron level precision, critical battery safety concerns necessitating 100% inspection. Manufacturing at scale demands a faster throughput, zero defect expectations for safety critical systems. So all this, because of all this high demands in the manufacturing, traditional inspection methods can't meet these demands, creating perfect application for Rust-powered machine vision systems that combines performance with the memory safety guarantees that. Why Rust? The characters that are mentioned above makes the Rust uniquely suited for EV manufacturing where reliability, speed, and safety cannot be compromised. The first characteristics that we can consider is memory safety. Zero memory related crash in a production system through compile time guarantees critical for 24/7 manufacturing environments where downtime costs thousands per minute. Fearless concurrencies, safely processing multiple camera feeds simultaneously without data race conditioning without any race conditioning, enabling real-time inspection across multiple assembly stages. And the rest performance is very close to C. Speeds with a zero cost abstraction allow processing of high resolution images at a line speed exceeding 10 parts per second throughput. FFI capabilities, seamless integration with CC plus vision libraries and a machine learning framework like TensorFlow and PyCharm while maintaining safety boundaries. The real-time inline quality inspection systems. The high-resolution component inspection that is quite often in the manufacturing environment. So Rust-powered vision system currently deployed in production environment achieves resolution down to 5 micron for critical cell inspections, processing speed of 12 to 15 frames per second at a 4K resolution, camera image resolution. Multi-spectrum imaging like visible IR and UV for comprehensive defect detections. Consistent performance under variable lighting conditions. These are all becoming very essential. And our multi-camera array leverage Rust's concurrency model to process multiple inspection angles simultaneously without frame drops. The next presentation is next slide, which is AI enhanced defect detection, which is part of the inspection systems, machine vision inspection systems, and in the EV manufacturing. So image acquisition, which is a primary part that has high-speed camera capture, capturing multiple views of components at line speed, like approximately like a 10 plus parts per second, which is significantly higher rate in the modern manufacturing. Preprocessing. Rust SAMD optimization enables real-time noise reduction, contrast enhancements, and then feature extractions. AI-based classification. Custom neural network detects subtle defect missed by traditional threshold-based systems. And then automated responses. Part rejection, reworkflow flagging, or process adjustments based on defect classifications. Our system have demonstrated a 37% increase in defect detection rate compared to conventional machine vision approaches, while Rust safety guarantees prevent the system crash common in C++ environments. And the next thing is a battery cell and a pack inspection. On this, electrode alignment verification is one of the critical process in the battery assembly, battery pack assembly, basically. So it means assembling a cell into a pack. Sub-millimeter precision measurements are demanded in this process for anode and cathode alignment using structured light patterns, and Rust high-performance image processing is vital here. Surface defect detection. All AI models identify microscopic cracks, dents, and contaminations that could lead to thermal runaway events. Detecting such defects are critical in the battery cell and pack inspections. Electrolyte filling verification. NIR imaging combined with the custom detection algorithm, ensuring proper electrolyte levels and distributions. Thermal anomaly monitoring. On the pack level, the IR cameras like FLIR, which is a Teledyne now, the IR camera integrates for early detection of hotspots during formation cycling, with Rust handling a real-time thermal mapping. Advanced inspection methodologies. Battery module level inspection is one of the critical process in the manufacturing. Our Rust-based system implementation implements several cutting-edge techniques like wire bond quality assessments using structured illumination, laser weld quality verification through structural analysis, thermal imaging during module pulsing to identify resistance anomalies and welding defects, 3D profile mapping to verify dimensional accuracy post-assembly. So Rust performance enable a real-time processing of these complex inspections routines without dropping a frame. Laser weld inspection requires a precise lighting and multiple specialized camera to identify microscopic defects. 3D vision systems for assembly automation. When it comes for assembly automation, the challenges are quite significant, especially how precisely we are able to detect the depth for multiple components in a 3D perspective, which plays a vital role. So depth sensing, time of flight cameras provides a real-time spatial data for robot guidance with 2 millimeter accuracy. And then the other type could be a dual camera setup with Rust optimized disparity mapping for high precision and component handling. We do use laser triangulation, basically a laser-based sensors that could measure up to submicron precision for critical alignment tasks like motor, stator assembly, those kind of processes. And then point cloud processing. Rust performance enables a real-time processing of dense point clouds for complex assembly operations. So once the assembly and then is done, the AI-powered vision analytics that plays a vital role in any high advanced manufacturing environment. Deep learning integration, with our Rust system, it leverages multiple AI approaches for neural networks for defect classification with very high accuracy, close to 100%. Unsupervised anomaly detection, identifying novel defect types. Transfer learning techniques to reduce training data requirements by 80%. Rust FFI capabilities seamlessly connecting to TensorFlow and then Onyx runtime. Interference optimizing through Rust enables the deployment of edge devices directly on the production line, eliminating network latencies. Then it comes to manufacturing execution systems integration. In MES, in the manufacturing environment, component traceability is one of the prime role of having MES. So OCR and the barcode reading are the primary and the critical process of traceability implementation. So OCR and barcode reading capability tracks every component from raw material to finished vehicles with 99% or even close to 100% read accuracy. Process verification. So vision system confirms the correct assembly sequences and component placements and integrate with the digital work instructions. So every critical process was implemented with this vision-based assembly sequence verification process step. So quality data aggregation, all this data, there's a tons of data that are being collected. All these data are getting aggregated into a one digital form, and then that will be tagged to every component that is being manufactured in this line. Regulatory compliances. It also helps to automate documentation generation for safety and certification and recall readiness. Rust reliability ensures these mission-critical systems maintain uptime exceeding close to 100%, essential for maintaining production flow and traceability requirements. So once the vehicle is assembled, when it comes for advanced driver assistance system calibration and the digital twin integration, here also it plays a critical role. So ADAS calibration involves our advanced vision system validates precise calibration for a forward-facing camera, for accurate lane detection, LiDAR sensors for comprehensive obstacle recognition, radar units for reliable distance measurement, surround view camera systems for enhanced parking assistance. Rust's unparalleled performance ensures complex calibration procedures that can be completed within under 90 seconds per vehicle in a high volume manufacturing line. So digital twin integration, so real-time vision data seamlessly integrates into factory digital twin, facilitating productive maintenance through insightful trend analysis that tracks each of the process equipments on the critical process line. Dynamic real-time process optimization, robust closed-loop control systems, efficient virtual commissioning of a new product line. Future directions and implementation roadmap. So current deployment, so battery and powertrain inspection systems with basic AI capabilities achieving 30% reduction in escape defects. Our near-term target is to integration of a multimodal sensing like a vision, ultrasound, and thermal sensors with advanced machine learning models capable of predictive quality assessments. In the midterm, fully autonomous inspection system with a self-optimized algorithm and automated root cause analysis are in cards. For a long term, the cognitive manufacturing system where vision and robotics and the process controls form a unified AI production ecosystem, which could be achieved in a long-term approach. Rust will remain our foundation with its ecosystem, maturing alongside these advancements to provide performance, safety, and reliability required for next generation EV manufacturing. That concludes my presentation. Thank you all for your time and attention today. I truly appreciate your participation and I hope the session gave you valuable insights into AI-powered mission in Rust language. Thank you.